Good morning, guys. I hope you're all doing as well as can be expected. Today I'm having a look at an OCR question, an OCR A question from the periodic table elements in physical chemistry paper from 2022. And I've opted to do this question because I was asked to do some questions on harder, ligandy sort of questions. And I think that some of the OCR questions are a bit harder in this respect than the AQA ones. I've chosen this one because of the second part of this more than anything else, but it's also important that we can do things like part I, where we're having to explain why the ethane 1,2-diamine can act as a bidentate ligand. But the bit that I'm interested in is drawing complex ions, whereby we're having to identify how they can be both cis and trans, but also show an optical isomer in there as well. The bit that is a little bit weird is working out the empirical formula of the complex ion. That's something I've never seen AQA do, but here we are seeing it in an OCR paper, and I guess there's nothing to stop AQA from doing that if they wanted to. But yeah, this ethane 1,2-diamine, which I suppose you could call 1,2-diaminoethane, same thing. This is an example of a bidentate ligand that you will need to know if you're studying both OCR and AQA. I guess the bit that is a little bit different is how we can show these ligands when we draw them in the complex ions. In OCR, they want you to show the hydrogens on the nitrogen, which is, I guess, a more accurate way of using skeletal formula to represent this structure. In AQA, we tend to not put those hydrogens on there, and we just tend to go N, the C, H2, the C, H2, and then the N, like that. And I don't know why we do that in AQA, because that's not really very accurate, because you should always show the H's on everything other than carbon. With OCR, they do it, I guess, a bit more like it should be. And I guess even though this question is asking us why the ethane 1,2-diamine can act as a bidentate ligand, more generally we need to understand why any such example they might give us can act as a monodentate ligand, a bidentate ligand, a multidentate ligand. So it's, yes, obviously we want to make it specific to this exact example, but any bidentate ligand is such because it can form two coordinate bonds with the central transition metal. But I guess that's not really sufficient enough, because it's the fact that there are two different atoms within the ligand that will have a lone pair. And the example that it's good to come back to is water, because the oxygen atom in the water molecule will have two lone pairs. But water is a monodentate ligand because the oxygen can only use one of those two lone pairs to form the coordinate bond. Because if we think about, and it'll make more sense, I guess, when we draw some of these down here, how can you have one atom forming two coordinate bonds and therefore existing in more than one sort of position around your octahedral shape? That doesn't make sense. So it's not just a case of we need there to be two lone pairs, we need there to be two different atoms that each have a lone pair. So obviously in the ethane 1,2-diamine, it's the two nitrogens that are going to have the lone pair. So you'll have one coordinate bond coming from there to your central transition metal and one coordinate bond coming from there. So I guess we do need to be a bit specific in that sense. So it contains two N atoms that each have a lone pair of electrons, and then generally any ligand, whether it's monodentate, bidentate, multidentate, will be able to donate that lone pair of electrons to the central transition metal. I know donate's a bit of a weird word when we're thinking about a type of covalent bond, but it's just the idea that the transition metal is not going to be sharing one of its electrons with one from the ligand, hence they are coordinate bonds or dative covalent bonds, so the word donate is what we would use there. And so obviously for monodentate ligands, it would be that you've got one atom that has a lone pair that can be donated to the central transition metal ion. If you've got a multidentate ligand, that would class as anything greater than 2. Or I think polydentate is also a word that might get used, particularly in OCR. But anything with more than 2 atoms that have lone pairs would fall into that category. So EDTA is the probably most common example that both OCR and AQA will need to know, whereby one EDTA 4- ion has 6 atoms that each have their own lone pair. So there are 2 nitrogens and 4 oxygens that each have a lone pair that they can donate. Okay. Now, thinking about using this bidentate ligand, it says the iron 3 ion, so that's obviously going to be important, forms a complex ion A that has 2 of these ethane 1,2 diamine ligands and 2 chloride ion ligands. So we've got 2 bidentate ligands, 2 monodentate ligands in our Cl- ions. It says it can have cis and trans isomers, or stereoisomers, and that one of those stereoisomers can then exist as optical isomers. So we've got to determine the empirical formula with charge of complex ion A, and then draw the 3D structures of the 3 stereoisomers. So I guess the first thing, I'm not going to write it empirically straight away, is to recognise that we are going to have, with 2 ethane 1,2 diamine ligands and 2 chloride ion ligands, an octahedral shape. 6 coordinate bonds in total, 4 from the bidentate ligands in total, and then 2 from the monodentate ligands in total. So the complex ion A would have the formula Fe bracket H2NCH2CH2NH2, 2 of them, and then 2 chloride ion ligands, so Cl2. Now, in terms of the overall charge, this is something that I know can prove problematic for students. You need to know the oxidation state of the transition metal, and we do. We then also need to know the charges on some of the sort of known examples for our ligands. So we need to be aware of the fact that this is a neutral ligand, and we need to be aware that the chloride ion ligands are not neutral. Water, neutral. Ammonia, neutral. The other bidentate ligand example would be our ethane dioate ions. They have a charge of 2-. EDTA has a charge of 4-. They're the ones I would want you to know. So then if the ion has a oxidation state of +3, these are neutral, these are each -1, +3, -1, -1 gives me +1. So that would be the charge on the complex ion A, which we're also going to need when we're drawing them out in a second. Now, the empirical formula is just going to be, first of all, collating all of these like terms, and we're not going to be able to simplify sort of a molecular formula because we've only got 1 ion. So the empirical is going to be the same as sort of the molecular. So 1 ion, and I don't suppose it matters what order we do this in. So chlorines, carbons, nitrogens, and then hydrogens. Except that is really bad maths on my part because we've got 2 of those ligands. So that therefore means I need to go with 4 carbons, 4 nitrogens, and then 2, 4, 6, 8 times 2, 16 hydrogens. And then it also wants the charge. Feels a bit weird to put a charge on an empirical formula. I'm going to go with brackets and put the charge there. So FeCl2, 4 carbons, 4 nitrogens, and then 16 hydrogens. And we can't simplify that because we only have 1 ion. So that's the simplest ratio. So we know it's going to be octahedral, and when we have octahedral shapes, there are two ways we can get cis and trans stereoisomers. We can either have two different types of monodentate ligand in the ratio of 4 of one and 2 of the other, and the example of that would be your copper 4 ammonias, 2 waters, the deep blue solution. The other way we can get cis and trans isomers is by having this combination of 2 bidentate ligands and 2 monodentate ligands. So we're kind of going to be thinking about where the monodentate ligands are to decide if it's going to be cis or trans. So the way that I would always go about drawing these, and this is just probably I don't want to say a me thing, but you don't have to do this, absolutely not, is I'm going to pop my iron in the middle and then kind of just set up the 6 bonds to make my octahedral shape. Oops, why have I done that as a... I feel like I'm losing my ability to talk and do at the same time. My apologies. So then in terms of the first thing, I'd be thinking about our cis and trans stereoisomers. So for the chloride ion ligands, if we want to put them as in the trans arrangement, that's basically suggesting that they need to be as far apart as possible, which in an octahedral shape is going to be 180 degrees. Now, there are different ways we can achieve 180 degrees, but I know in my head, and I'm sure in some of yours as well, it makes more sense to put them sort of in the axial positions, top and bottom. But these two positions, for example, are also 180 degrees apart. These two are also 180 degrees apart. So there are options, but for me, that makes more sense. And then we can put on the bidentate ligands. And so they would go, it would be the nitrogen atoms that would have the lone pairs. And then carbon, carbon to nitrogen, carbon, carbon to nitrogen, and then H2, 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 H2. So that is then going to be the trans isomer. And so in order to then turn that into a cis stereoisomer, the cis part is referring to the 2 chloride ion ligands, the 2 monodentate ligands, being adjacent or being only 90 degrees apart. So again, we have got options here because within an octahedral shape, the 4 positions around the middle, aka sort of like the square planar bit, they're all 90 degrees apart from each other. But then also the axial positions are then also going to be 90 degrees from the ones around the middle. So again, different ways we can do this. I'm going to leave the chlorine at the top, and then I'm going to move the second one to one of the positions around the middle like that. And then that leaves me with these 4 positions to pop my bidentate ligands. So again, carbon to carbon, carbon to carbon, and then pop my H2s on there like that, and that is our cis stereoisomer. And like I say, there are different positions you can put them in, top and any of the ones around the middle, or 2 adjacent around the middle. Now only one of those is going to have an optical isomer, and if we think about drawing a mirror image of each of these and reflecting this image over here or reflecting this image over here, this is going to give us the exact same image in the mirror. So those mirror images will be superimposable because nothing is going to, I guess, change because of where we've got the chloride ions and the ethane 1,2-diamine ligands in that structure. Whereas if I flip this one in the mirror plane, they're not going to be superimposable mirror images. So this is the one that then is going to exist as the optical isomer. And so I'm going to imagine that I've taken my cis isomer and then I've got a y-axis mirror plane so that the chlorine at the top stays in the same position, but this one's now going to be here. And then again, the bidentate ligands will fill the other spaces. I guess it's up to you which box you choose to use, obviously, for each ligand. They haven't specified. They haven't said you have to label which stereoisomer is which. I opted to do the cis and trans here and then the optical one underneath, but I guess the maybe issue with that is it might be harder to draw the optical isomer. So I guess the bit that you might kind of come to know when you see another question like this is the trans one, when you have this combination of ligands, will never be able to give us optical isomers. So it might have been that you wanted to put the trans one down here, draw the cis one here, and then draw the non-superimposable mirror image here. Like, it really doesn't matter from a marking point of view, it's just what makes life easier for you. And then the one thing that I now need to do that I've got all my structures is square brackets and then pop the charge on. So we worked out that it was plus and then plus. And I guess it's very easy to forget to do this bit, which would be a real shame in terms of you would definitely lose some of these marks if you were to forget to do your square brackets in your charge. And that's that. So hopefully that all makes sense. I have seen quite a few OCR questions where they've got you to think about cis trans and then the optical component of that together. AQA, it tends to be more one or the other, but there is nothing to stop them from opting to do something like this, and it's always good to be prepared. So hopefully that makes sense, everyone, and if it doesn't, as always, just let me know, send me a message, leave a comment on the video. And if there's any similar looking questions or other questions you want me to make sure that I get done before Monday, then, well, Tuesday's the exam, but yeah, get them done sort of by Monday, then just let me know. Thank you so much for watching, guys, and please take care of yourselves. Bye!